Welcome to Chapter 8 on K-nearest neighbors. In this chapter, we explore one of the simplest and most intuitive methods in all of machine learning. K-nearest neighbors, almost always shortened to KNN, is among the easiest methods to explain to someone who has never seen a model before. Its principle fits in one sentence. Points that sit close together in feature space tend to share outcomes. By the end of this chapter, you should be able to explain the basic idea of KNN in plain language, describe what it means for a method to be distance-based and lazy, use KNN for classification and regression, explain the role of K, and compare distance metrics like Euclidean and Manhattan. You should also be able to explain why feature scaling is essential for KNN and apply it. Choose K with a validation set or cross-validation and train and evaluate KNN models in Python using a clean pipeline. This figure shows the core idea. To classify the query point, the black square, KNN takes a majority vote among its nearest training neighbors inside the dashed circle. Here the circle holds more Class A points, so the query is labeled Class A. KNN rests on a single assumption that turns out to be surprisingly powerful. Similar inputs lead to similar outputs. What makes it so approachable is that it mirrors the way people naturally reason. KNN belongs to a family of methods called lazy learners, and the name is more flattering than it sounds. Contrast this with the methods from earlier chapters, which do their heavy work up front during training. A lazy or instance-based learner defers computation until prediction time. It simply stores the training examples instead of summarizing them into a model. KNN is the classic case. There is no learned model beyond the data itself. This trade-off is perfectly fine when the training set is small or when predictions are made only infrequently. Everything in KNN hinges on measuring how far apart two observations are. Picture a customer data set with just two features, age and annual income. The most common choice is Euclidean distance, the ordinary straight line distance you would measure with a ruler. For many features, it generalizes naturally. Take the difference in each feature, square it, sum across all features, and take the square root. A second common choice is Manhattan distance. Instead of squaring the differences, it simply adds up the absolute differences across the features. Here we see the two most common distance metrics for KNN side by side. Here is the mistake that quietly ruins more KNN models than any other, forgetting to scale the features. The fix is to put every feature on a comparable scale before computing distances, using either standardization to mean 0 and standard deviation 1 or normalization to a fixed range. The key point is to always scale your features before measuring distance. The cleanest way, without leaking information from the test set, is to wrap the scalar and the model together in a scikit-learn pipeline, so the scalar is fit only on the training data inside each fold. The single knob that shapes a KNN model is K, the number of neighbors allowed to vote. When K is very small, the model listens to only a few nearby points. When K is very large, it averages over a wide crowd. This illustrates how K moves the model along the bias-variance trade-off we met back in Chapter 5. To choose K, try several values, score each on a held-out validation set, or better, with cross-validation, and keep the one that performs best. One practical tip. In a two-class problem, an odd K avoids tie votes, so 3, 5, and 7 are popular starting points. Everything so far has been described in words. Let us now work through a concrete example. A tutoring center keeps records on students preparing for a certification exam. Here are 6 past students, each described by 2 features and their exam result. This small table is the entire training set for our hand calculation. Let us start the naive way, plugging the raw feature values straight into Euclidean distance without any scaling. This is the distance formula for our example. We measure each past student's distance from the new student whose study hours and problems solved are 8 and 120. Take the first student as a worked instance. The study hours gap is -6 and the problems gap is -80. So the distance is the square root of 36 plus 6400, which is about 80.2. This table lists the Euclidean distances from the new student to each past student using the raw unscaled features. The 3 nearest turn out to be students 6, 4, and 2. Sorting by distance, the 3 nearest neighbors are student 6 at 30.3, pass, student 4 at 40.4, pass, and student 2 at 60.1, fail. But look closely at what actually drove that ranking. To give both features an equal voice, we standardize each one to have mean 0 and standard deviation 1. Here is the same data after standardizing each feature. Now a 1-unit move in study hours counts exactly the same as a 1-unit move in problem solved. Now let us recompute the Euclidean distances, this time using the scaled coordinates. After scaling, the 3 nearest neighbors are students 6, 3, and 2, and notice that the vote has changed. Same data, same query, same k, and the same distance formula, and yet the prediction flipped from pass to fail. This is the whole argument for scaling in one example. K&N never knows that problem solved happens to use bigger numbers than study hours. It only sees distances. Unless you scale, the feature with the larger numeric range silently decides who counts as a neighbor. Let us look at this visually, showing the scaled data with the new student and her 3 nearest neighbors circled. This figure shows the hand calculation in standardized feature space. The dashed circle now holds student 6, a pass, but also students 3 and 2, both fail, giving a 2-to-1 vote for fail. In classification, K&N makes its decision by majority voting among the neighbors. A useful refinement is distance-weighted voting, where closer neighbors carry more influence than far ones. K&N handles regression with almost the same machinery, swapping the vote for an average. With k equal to 3, if the 3 nearest apartments sold for 300, 320, and 340,000, the prediction is simply their average, 320,000. This figure summarizes the K&N prediction procedure. K&N does no real training. At prediction time, it measures the distance from the query to all stored points, keeps the k closest, and combines their labels by voting or averaging. The curse of dimensionality is the tendency of distance-based methods to degrade as the number of features grows. In high-dimensional space, points become roughly equidistant, and the very notion of nearest loses its discriminating power. There are several remedies. Select only the features that matter and drop irrelevant ones. Apply dimensionality reduction, such as PCA before running K&N, or consider a model better suited to high-dimensional data, such as a tree ensemble. It is worth connecting K to the bias variance trade-off from Chapter 5, since K&N is one of its clearest illustrations. A small k gives a wiggly boundary with low bias but high variance, while a large k is smoother with high bias but low variance. Choosing k is therefore not a side detail. K&N earns its place in every introductory course because it is honest about what it does. Its strengths are clear. It is easy to explain to non-technical audiences, simple to implement, works for both classification and regression, makes almost no assumptions about the shape of the data, and can trace curvy, nonlinear boundaries that linear models cannot. Its weaknesses are equally real, and most trace back to its reliance on distance and stored data. Prediction is slow on large datasets. It is highly sensitive to feature scaling, easily misled by irrelevant features, degrades in high dimensions, and must keep the entire training set in memory. Performance also swings with the choice of k and the distance metric. In short, KNN is an excellent teaching tool and a fine choice for small to medium problems with a handful of well-chosen, well-scaled features. Let us put this into practice classifying penguins. Notice that the 4 measurements live on very different scales, with flipper length in the low 200s of millimeters and body mass in the thousands of grams, so scaling here is essential. This code loads the Palmer penguin's data, picks 4 body measurements as the features and species as the target, splits the data into training and test sets, and builds a pipeline that scales the features and then applies a KNN classifier with 5 neighbors. In short, the pipeline first standardizes every feature to mean 0 and standard deviation 1, then hands the scaled data to a KNN classifier using 5 neighbors. Rather than trusting a single guess of k equal to 5, let us scan a range of values and let cross-validation pick the winner. This code loops over k from 1 to 15, builds the same scale then classify pipeline for each value, and uses 5-fold cross-validation to print the mean accuracy at every k. Watch how the accuracy rises plateaus, and may even dip again as k grows, which tells us where the sweet spot lies. Now we turn to KNN regression on California housing. This code loads the housing data, splits it, and builds a pipeline that scales the features and applies a KNN regressor with 5 neighbors before fitting and predicting. The prediction for each district is simply the average target value of its 5 nearest neighbors, measured in scaled feature space. Consider a case study. A regional clinic wants a quick second opinion at intake. A nurse records routine measurements such as age, blood pressure, heart rate, and a couple of test results, and the clinic has years of past visits on file, each labeled with whether the patient needed urgent follow-up. KNN fits this setting almost too neatly because it works the way a thoughtful clinician already thinks. Find the patients who most resemble the one in front of you and see how they fared. Used as a transparent prompt rather than a verdict, it offers an early warning aid a doctor can follow. The following code cross-validates a KNN classifier on the breast cancer dataset used here as a proxy for clinical triage decisions across 6 different values of K. This code loads the breast cancer data, splits it with stratification, and then for each candidate K, builds a scale then classify pipeline and records its cross-validated F1 score, keeping track of the best performing K. To summarize, K nearest neighbors predicts by looking at the company a point keeps. Distance is the engine of the method, with Euclidean and Manhattan the usual choices, and because distance depends on scale, feature scaling is essential rather than cosmetic. For further reading, look to introductory treatments of instance-based and lazy learning, the scikit-learn documentation on the KNN classifier and regressor, discussions of the curse of dimensionality, and applied examples of KNN in classification and recommendation systems. That brings us to the end of Chapter 8 on K-nearest neighbors. Next, we build on these ideas in the chapters that follow.